Okay, so today we're going to be starting really the first major calculus idea, which is a limit. We're kind of shifting away from the pre-cal review and now getting into the first actual calculus. Limits are a little bit weird at first, but the more you do it, the better you'll get, and really they're not too bad. We're going to do limits three ways. Today we're going to do limits numerically, that just means with table. We're going to do limits graphically, spoiler alert, that means with a graph. And then we're going to start the easiest types of the analytical or the algebraic ways of evaluating a limit. So we're going to knock out the two easy ones, then we're going to start this third one, which gets harder, but we'll really continue with this in the next video also. Anyways, here's your limit notation. I don't think you really saw it last year, but typically you would see it at the end of a pre-AP pre-cal. And limit is more or less the behavior of a function. It kind of tells you where is that function trending towards, what is the pattern going on with this function or with this graph. So here's the limit notation. You can see with the bullet points, that's how it's read kind of verbatim. And so how you translate it from the math into the English language goes like this. The limit of your function, f of x, as x approaches a. So you always have to have your limit notation. Then you have to tell me what you're taking the limit of. Typically, it's whatever function you're dealing with. Then you need to indicate your target x value, right? You need to know what general area of the function you're looking at. So you need to know which x value you're going to send it closer towards. It's kind of what I refer to as the target. Anyways, the limit of f of x as x approaches a is equal to L. Right, so there's the mathematical language, and then here's the translation into English. Another way to think about a limit is you could read it like this. As the x values get closer and closer and closer to a, your target, the graph, or the function, or the y value, correspondingly is going to get closer and closer and closer to L. So as your x values approach some specific location, you're going to be looking at what the y values are doing. Right? And three ways to do it. With the table, which we're going to do first, then with the graph, which we're going to do, and then analytically or with algebra. We're going to start this at the tail end of this video, then we're going to continue on and do the harder stuff next time. Okay, an important note, continuity does not affect the limit. We'll kind of talk about this a little bit more, and we'll deal with the formal definition of continuity at the end of this packet. But continuous means, can you graph it without picking up your pencil or your pen? But whether the graph is continuous or whether it has this little point that's kind of somewhere else or whether it's completely undefined at a specific spot, the continuity isn't going to affect a limit. Okay, so let's look at some more notation. This is the overall limit notation, but we also have specifically one-sided limit notations. And of course, the one side would be the left side and the right side. So let's go through and look at these notations. The left-sided limit notation, we would write it as the limit of your function as x approaches a. That's your overall notation. To indicate that you only care about one side, what you're going to do is put a little negative, kind of like an exponent, on the a. So that shows you that you really don't care about as x gets closer to a overall, you're only caring about x getting closer to a, but from the negative side of a, which means the left, right? So the limit of your function as x approaches a, and then that little minus sign kind of being there like an exponent indicates that it's only from the left. The right-sided limit notation is going to be similar. Oops, let me do this one in red so that we can differentiate between them. The limit, come on red pen, the limit of your function as x approaches a. Now instead of a minus sign, as the little kind of exponent-ish thing, we're going to put a plus sign. Okay, so we have the overall limit notation, which is what you have when there's no minus, there's no plus. That's really thinking about both sides, but then we also have the strictly one-sided. We have the left side and we have the right side. Now, that's a little bit long as far as writing out notation. So for my class, I'm okay if you use this shorthand. L subscript L, that's Mr. Bell's shorthand for limit from the left, and then L subscript R, that's limit from the right. I'm okay if you do these for my class but if you're on the AP exam, you would need to use the formal notation. Okay, so we have the limit from the left and the limit from the right. I'm okay if you use those for my class. And then we have that overall limit exists. Remember, the overall limit notation looks like this, where there's no plus or there's no minus. That means you really want to check both sides. And that overall limit is only going to exist if the limit from the left equals the limit from the right. If those two things do not match, then the overall limit will not exist. So if the left side and the right side are two different numbers, then that overall limit is not going to exist. And you say does not exist. All right, so let's go back and look at the continuity just really quickly. Let's look at these three examples, and let's kind of see how these limits all match regardless of the continuity. So we'll do the left side in blue, then we'll do the right side in red, and we'll see how the overall limit is going to be the same. So the limit, what you're concerned with here from the left is as x approaches a from the left. So we're going to approach a from the left. That means you need to just pick a point on the function, right? Here's your target destination where x is a. You need to pick a target point on the left of that spot, and then you're just going to ride the function back towards your specific x value, right? My x value that I'm investigating is a, so I'm going to start on the left side of a, and then we're going to ride the function back towards your target, and you're trying to see what's the pattern or what's the trend, what are the y values getting closer towards. As the x gets closer to a, so as that graph approaches from the left, what is the y value getting closer to being? And it looks like this function is trending you towards this solid point, and this point has a y value that's written as L. Sorry for the bells, they're still going. So here we know the limit from the left is L. As the x values approach from the left, the y values are getting closer and closer to this point, and the y value of that point is L. Now let's do the right-sided limit. So we're going to hop on the function on the right side. Remember, here's my target. I'm going to hop on the function on the right side, and then I'm going to ride the function back towards my target value. And it looks like as the x gets closer and closer and closer to a, the y values, it goes up, but then the y values start coming back down. The y values are going to get closer and closer and closer to this point again. And that point has a y value of L. So we have the limit from the right is also L. So since the limit from the left and the limit from the right, since those are both converging to that same location, right, those two arrows are meeting together, that is a sign that you know the overall limit is going to exist. If these two numbers match, that means the left side and the right side are approaching the same location. That means your overall limit, as x approaches a, is going to exist, and it's just going to be that value. Now let's look at the next one where the point has been removed. Again, we're going to approach a from the left. So I hop on the function, ride it back towards my target x value. Again, it looks like as you ride this function back towards your target, it's taking you towards this spot. And that spot has a y value of L. Right? Starting on the left side, coming back towards my target. So I hop on the function, ride it back, and it looks like it's trending towards this spot, and then the y value of that spot is L. Let's look at the limit from the right. Again, we're going to approach a from the right. So I'm going to hop on this function and then come back towards my target, and it looks like my function is trending me towards this point again. So look, the limit from the left and the limit from the right, those are both converging towards this same location. Now the point isn't filled in there. The point is actually somewhere else, down here. But it doesn't actually matter what happens at that instantaneous value. The limit is more about the trend or the behavior around that value. It's really telling you where is that function supposed to be. And if you look from the left, it's trending you towards that point. If you look to the right, it's trending you towards that point. So this is really where the function is supposed to be. The fact that it's somewhere else does not affect the limit. Here, this overall limit, as x approaches a, would still be L. That this point is somewhere else doesn't change, right? Because the function is still trending you towards that same location. And it's going to be the same thing over here on this third one. As you approach from the left, it's taking you towards this location. as you approach from the right, it's also converging to that same location. The function's completely undefined. There is no solid dot, but it doesn't matter. The solid dot could be there where it's supposed to. It could be somewhere else, or it could be completely undefined. It wouldn't matter. The limit is all about where that function is supposed to be. And since the limit from the left and the limit from the right, since those match, since they're converging towards that same spot, the overall limit does exist, and it just is that number. Right? So the limit is like the behavior or the trend of a graph. What actually happens at the point is irrelevant. The limit is all about the behavior as you get closer and closer and closer. Okay, so we're now going to shift gears and kind of start investigating things with the table, which means numerically, and then we'll get into some graphical ones. All right, so get out a calculator. If you don't have one, you can use Desmos or use an emulator on your phone. But here we're going to get a calculator, and we're going to look at the behavior of this function. Specifically, we're going to look at what happens as x gets really, really, really close to -3. All right, so the first thing we got to do is go to my calculator. I'm going to type in this function into the y1. All right, get out of there. So type in this function. Remember your parentheses. So I've got square root x plus 4. Get out of the square root, -1, and then x plus 3. Okay, let me just check the graph. Yesterday I was having a lot of trouble trying to record this. Kept typing the function in wrong, which was frustrating. But I got it in right this time, which is wonderful. Okay, so I'm going to quit out of the y equals. Now, if I wanted to actually plug in -3, which means to direct evaluate it, I could do vars, y-vars, function mode, y1. I could tell this function to evaluate at -3, but you're going to get an error, right? If I plug in -3 into this function, you're going to get a 0 in the denominator, which is a domain issue, right? So here, that function is undefined at that specific point, but we really don't care. We want to know what happens as I get closer and closer and closer. So that instantaneous value is undefined, but we can still look at the pattern and at the trend as I approach it from the left and then as I approach it from the right. And that's what a limit is doing. Not what's actually happening at the point, but what's supposed to be happening based on the trend as I get closer from the left and then as I get closer from the right. And if those two one-sided limits match, then the overall limit exists, and it's just that number that both one-sided limits are. All right, so let's go to this table and let's fill it out. Let's get out of here. Now, if you hit second graph, you can go to your table, and that table is generally going to be populated by your integer values, but we don't really have integer values, so I'm going to go to second, and then window, which is my table set. And I'm going to change this table so that instead of the independent variable being automatically generated, I'm going to change it so that it's only asked, right? I'm only going to want the x values that I ask for. And then if I go back to the table, it's going to be blank, and then I can plug in whatever x values I want. So here we've got that first one. When the x value is -3.1, it looks like that y value is 0.51317. Now, -3.1 is pretty close to -3. It's just 1/10 to the left. Let's see what happens if I get closer, right? That's pretty close, but it's 1/10 away, 0.1. Let's see what happens if I get closer. This one's only 1/100th of a unit away. So let's see what happens. -3.01. It looks like that y value is 0.50126. So I started off on the left side, then I got closer. Now let's get even closer still. And it looks like that one is 0.50013. So let's see if there's any pattern. As the x values approach -3 from the left, so I started off on the left side, but then I got closer and closer and closer to my target. Was there any pattern, or is there any trend? Does it look like these numbers are approaching anything in specific? Yes. if you follow these three numbers, it looks like they're getting closer to 0.5. So that numerically tells us that the limit from the left, right, as your x values approach your target from the left, you're looking for the corresponding pattern in the y values, and those are getting closer to your 1/2 value. Now let's do the limits from the right. Right, so let's go slightly to the right of -3, and then we'll get closer and closer. Remember, the x values kind of tell you where to look, but it's actually the pattern in the y values that you're looking at, right? That's where the answer is going to come from. So let's do -2.9. Let's see if this is going to work. So we got 0.48809. Let's get closer to -3. -2.99. 49876. And then let's get even closer. 2.999. And then that's 0.49988. Okay. So I approached from the left, and it looked like there was a pattern with those corresponding y values. So the limit from the left was 1/2. Then I'm going to approach from the right. It does look like there's another pattern, right? These three numbers, as I start farther away and as I get closer, it looks like the limit from the right is also going to be converging towards that 0.5 value. Since the left is approaching 0.5 and the right is approaching 0.5, then I know that this overall limit is going to exist, and it's going to be that 0.5 for the 1/2 value. Right, so the x values tell you where to look, right? The -3 is my target, and what actually happens at your target doesn't matter. You're really interested in, hey, that little area to the left, and then that little area to the right, and then is there a corresponding pattern, and then do those patterns match from both sides. Let's look at the graph to try to confirm this. I'm going to change the window really quickly because I know the standard -10 to 10 doesn't really get a good picture of the graph. I'm going to do, how about -5 to 1, and then 0 to 3 is probably fine. So if you were to look at this graph, it's going to start here at -4, 1, and then it's going to look something pretty similar to this, except the calculator is kind of misleading you. Remember back, if I were to actually go to the table, and if I were to plug in -3, remember, you get the error. It can't divide by 0. So really, there's not a solid point when x is -3. There's actually going to be a little hole right there. So here at -4, the height of the function was at 1. But then at -3, right, this function is decreasing. Then you have this little hole. Then it's decreasing again. We had the limit from the left. We knew, hey, as that function approached from the left, those values were getting closer to 1/2. And then we have the function from the right, which means, hey, as those x values get closer to my target from the right, we know those y values were also getting closer to 0.5. So that tells us that the y value of this hole is actually going to be 1/2. The function is undefined there, but it's supposed to be at a height of 1/2. That's what the limit tells me, the behavior, where that function is supposed to exist. All right, let's move on to the next one. Make sure your calculator is in radian mode, since we have trig. Always, always, always radian mode for me. Here I'm just going to do, watch out for the keyboard, second plus 712. Oops, I got to get out of the graph. Okay, so second plus 712. I just always like to clear the memory. It's really nice, and when you do that, it'll reset to radian mode. And then let's go type this sucker in. Sine of 4x divided by x. Okay, now this table doesn't come pre-populated as far as the x values, so let's think. I want to investigate what's happening in that area around 0. Right? So 0 is kind of what I want to see. Now, if you actually were to plug in 0 into this function, you're going to get another error because you can't divide by 0. but it's okay. It doesn't matter if you're undefined at that one specific spot. You're trying to see, hey, if I start to the left side of 0, but then I get closer, is there a pattern? Or if I start on the right side of 0 and then I get back and closer to 0, is there a trend? And then we're going to be checking, do those two things match? Do they converge to the same location? Now you could pick any values, right? You could do -10, -3, -1. Those values would start on the left side and then get closer. And then you could do something like 17, 5, and 2, right? You could pick any values you want on the left and then get closer, on the right and then get closer. But look at the previous example. I didn't go very far to the left. I didn't go very far to the right. You only need to go like minuscule in each direction. So how about we do something like this? Like how about -0.1, that's on the left side of 0, but then I'll get closer. -0.01, -0.001. If you were to do something like -10, -5, -1, the pattern with the y values may not be as obvious. You want to pick x values that are pretty close to your target. Then let's do the same thing on the right. 0.1, 0.01, 0.001. Now let's go to the table and let's type these things in. Change the table set back to ask. Okay, here we go. Starting on the left side, but then we're going to get closer and closer and closer to my target. So -0.1, -0.01, -0.001. So it looks like as I start on the left side and then get closer and closer and closer, looks like that y value kind of started as 3.8942, and then the y value got 3.9989, and then the table says 4. Well, if I actually scroll over to it, it's not 4. The table just only has room for 5 digits, and since this one's 3.9999, and even that next one would round to a 9, the calculator just doesn't have enough space to write out all of those different decimals. So it's just saying, screw it, okay, we're going to round it and we're going to call it 4. But it's not 4, but it's really, really, really close to 4. So 3.99989. So let's look at this limit from the left. The x value started on the left, but then got closer to my target. Was there a corresponding pattern with the y values? Does it look like these things are getting closer to anything in particular? Yes, it certainly looks like those things are getting closer and closer and closer to 4. Now let's check the right side and see if it's going to match. So let's do 0.1, 0.01, 0.00, oops, 1, yeah, there we go. And this graph is actually symmetrical, so you're going to see you have the same exact values, right? So here, if I plugged in the 0.1, it's going to be the same as the -0.1, 3.8942, and then this one would be your 3.9989, and then this one, the calculator is rounding it, it's going to tell you 4, but really it's 3.99989. So as my x values started on the right side of my target, but then came back closer to it, is there a trend with those corresponding y values? Yes, it looks like those are also getting closer to 4. Both sides of this table are converging to a location of 4. So the overall limit is going to exist, and it is 4. Let's look at the graph. Here I just changed the window a little bit. You see it's not really a typical sinusoid. It kind of has that same kind of oscillating behavior, except it gets really narrow, really kind of shallow as you go farther away from the y-axis, and then it's steeper up here. We would call this a sinusoid that goes through dampened oscillation, right? All of those successive hills and valleys are going to be closer and closer and closer to the x-axis because you are dividing it by something, right? So this graph, it's undefined at 0. Oh, come on, pencil. And then it's going to do something more or less like this, right? It goes through that dampened oscillation. It looks like a sinusoid, except each hill and each valley gets a little bit less big. Oh my gosh, come on, pencil. And then it does the same thing on the left. But what we checked with this table was that the limit from the left, right, as the x values started negative and then got closer and closer and closer to 0, those y values were getting closer to this point, which is up at 4. Then we also checked from the right, and those values, right, as you started on the right and then got closer, those y values were getting closer to 4. So even though this point is undefined and it does not exist on your graph or in your function, I know the y value for that hole is 4. That's where the function is supposed to be because that's what the limit tells us. Alright, so that's all with the limits from a table. Let's shift and start doing them graphically, which we've kind of been doing already. But let's go through and do these quick. First thing would be to sketch the graph if you don't have it. So here I can see I've got a piecewise function. It's going to mostly be this parabola. You're going to graph the parabola that's shifted up 1 unit for everything except x equals 2. Let's see, so it looks something like this. If you plug in 2 squared plus 1, that would be 5. So that's where the hole is going to end up being, at 5. But it says when x is 2, the point is actually at 3. So this graph looks something like this, right? It's mostly the parabola, except at that one spot where x equals 2, the value is 3. So let's check from the left. Right? As I hop on this function, remember, here's my target. My target is 2, right? The function, or the question, is going to always tell you what your target is. So as I hop on the left side and then ride the function back towards my target, it looks like my function is trending me towards that location. The fact that the point is somewhere else doesn't matter. The limit is all about the behavior. And as you ride this function back towards your target, it is taking you towards this point, which is at a height of 5. So the limit from the left is 5. Let's do the same thing from the right. Hop on the function on the right side, come back towards my target, and it looks like as you ride that function back towards your target, it's trending you towards this location. And that location is at a height of 5. So the limit from the left and the limit from the right, those are both taking you towards the exact same spot, and that spot is at a height of 5. So this overall limit does exist, and it is 5. The fact that the point is defined somewhere else doesn't matter. But you need your two one-sided limits to match. If these two were any different numbers, then the question would be, does not exist. Okay, the next one, we're going to have a step function. Remember back to the very beginning of these notes, we looked at something like this. We saw that was a step function. That was up at 1 or down at -1. Well, here it's just going to be shifted 3 units to the left. Right? So 1, 2, 3. 1, 2, 3. So a pretty quick and easy sketch once you know what this type of a function looks like, which you should, since we've done that in the notes already this year. So let's now investigate what's happening in and around -3. So I'm going to hop on the function. Here's my target, right? Hop on the left side, come back towards my target destination. Looks like if I start on the left side and then come back towards my target, it's trending you towards this spot. And that spot is at a height of -1. If I start on the right side and then I come back towards my target, it looks like it's trending you towards this location, and then that location is at a height of a +1. Do these two numbers match? No, they don't. The left side and the right side are trending towards two different locations, so this overall limit does not exist. And the reason why it doesn't exist is because the limit from the left doesn't equal the limit from the right.